Hi everyone, and welcome to this tutorial. Today, we are exploring the dot product, one of the simplest and most fundamental concepts in linear algebra. Despite its simplicity, the dot product is an essential building block in machine learning and artificial intelligence, powering many of the algorithms we use every day. To begin, let us define what the dot product is. The dot product is a way to combine two vectors and produce a single number. Mathematically, it is the sum of the products of their corresponding components. If we have two vectors, let us call them vector A and vector B, each with three components. The dot product is calculated by multiplying the first component of vector A with the first component of vector B, adding the product of the second components of both vectors, and then adding the product of the third components. This operation produces a single value. But what does the dot product mean geometrically? The dot product measures how much one vector aligns with another. It depends on both the magnitudes of the vectors and the cosine of the angle between them. If the two vectors point in the same direction, the dot product is positive and large. If they point in opposite directions, the dot product is negative. And if they are perpendicular, the dot product is zero. This makes it a powerful tool for understanding similarity, projection, and direction. In machine learning, the dot product shows up everywhere. In linear regression, it calculates the predicted value by combining the weights and the input features. In recommendation systems, it measures how similar a user's preferences are to an item's features. And in neural networks, it forms the core operation in each neuron, combining inputs with weights to produce an output. The dot product is also used in support vector machines, cosine similarity, and dimensionality reduction techniques like principal component analysis. Throughout this video, we will break down these applications and connect them to the dot product, showing why it is such a critical concept. By the end, you will not only understand the dot product mathematically but also appreciate its role in powering the algorithms behind artificial intelligence. Let us get started. Let us now dive into the mathematical calculation of the dot product with an example. Imagine we have two vectors. The first vector is 3, 1, and 4. The second vector is 2, 0, and 5. To compute the dot product, we multiply the first components of each vector, 3 times 2, which gives 6. Next, we multiply the second components, 1 times 0, which gives 0. Finally, we multiply the third components, 4 times 5, which gives 20. Adding these together, 6 plus 0 plus 20, we get 26 as the dot product. This single value, 26, tells us how much the two vectors align in terms of direction and magnitude. If the dot product had been 0, it would mean the vectors are perpendicular, or orthogonal, and have no alignment at all. If it were negative, the vectors would point in opposite directions. This geometric interpretation is critical when we use the dot product in machine learning. For instance, in recommendation systems, the dot product measures the similarity between a user's preference vector and an item's feature vector. A higher dot product means the user is more likely to be interested in the item. Similarly, in cosine similarity, the dot product is used alongside the magnitudes of the vectors to measure the angle between them, helping us quantify their similarity in a normalized way. Now that we understand how to calculate the dot product, let us see how it is applied in machine learning with a practical example. Consider linear regression, one of the simplest yet most effective machine learning models. In linear regression, the prediction for a given input is calculated as the dot product of the feature vector and the weight vector, plus a bias term. This means that each input feature is multiplied by its corresponding weight, and the results are added together along with the bias. For instance, if the feature vector contains values such as 3, 1, and 4, and the weight vector contains values such as 2, 0, and 5, the dot product of the two vectors is 26. Adding a bias, let us say 2, gives a final prediction of 28. This prediction represents the model's output for the given input. The beauty of using the dot product here is that it efficiently combines all the features and weights into a single value, which can then be used to make predictions. This same concept is used in neural networks, where each neuron computes a weighted sum of its inputs using the dot product and then passes the result through an activation function. Whether in simple models like linear regression or complex architectures like deep neural networks, the dot product is a fundamental operation. Another practical application of the dot product is in measuring similarity between vectors, particularly using cosine similarity. Cosine similarity is a technique that determines how similar two vectors are based on their direction, without considering their magnitude. This makes it incredibly useful in fields like recommendation systems, clustering, and text analysis. Cosine similarity works by dividing the dot product of two vectors by the product of their magnitudes. When the two vectors point in the same direction, the cosine similarity equals 1, indicating perfect similarity. If the vectors are perpendicular, the cosine similarity is 0, meaning no similarity. And if the vectors point in opposite directions, the cosine similarity becomes -1, showing perfect dissimilarity. Let us take an example. Consider two vectors, one representing a user's interest in different movie genres, and the other representing the genre features of a specific movie. If the user's vector contains values 1, 2, and 3, and the movie's vector contains values 4, 5, and 6, we first compute the dot product. This involves multiplying the first components, 1 and 4, the second components, 2 and 5, and the third components, 3 and 6, and summing these results. The dot product is 32. Next, we calculate the magnitudes of each vector. For the user's vector, this means squaring each component, adding them together, and taking the square root. The result is the square root of 14. For the movie's vector, we do the same, giving the square root of 77. Finally, we divide the dot product, 32, by the product of these magnitudes. This gives us the cosine similarity, which is a number between -1 and 1, representing how closely aligned the user's preferences are with the movie's features. This concept is also highly effective in clustering. For example, in document clustering, cosine similarity groups documents based on the direction of their word distributions, allowing us to identify similar content even in high-dimensional spaces. By combining the dot product with cosine similarity, we gain a simple yet powerful way to analyze and compare relationships in data. That wraps up our exploration of the dot product and its wide-ranging applications. I hope this tutorial helped clarify the concept and how it connects to real-world problems. The dot product is just one of many fundamental tools that opens the door to understanding more advanced topics. If you enjoyed this video and found it helpful, consider subscribing to the channel. By subscribing, you'll stay updated on new tutorials and resources that build on what we covered today. Your support helps us bring you more content that deepens your understanding of core concepts and their applications. Thank you for watching, and I'll see you in the next video.